If you have multiple devices, OpenCL actually allow you to migrate memory objects between devices. It's different from reading and writing a buffer. This call guarantees that memory objects will be located on another device when the command completes. And you can use this API to migrate multiple memory objects. And this API is called CL enqueue migrate memory objects. We're not going to go into the details because in most of the cases we have one device, so we may not have a lot of need of this migrate objects in our course. Now let's talk about host accessible memory. When you create a memory object, you can use a flag to specify that this memory object should be created in a host accessible memory. Now, the host accessible memory is not necessarily on the host. If on the device side you have a memory space that is accessible to the host, you can also assume that OpenCL can use that part of the memory. This host accessible flag requires that the allocation has to be mapped to a space that is accessible to the host. Oftentimes, if it is on the device side, this part of the memory should be mapped into this memory address space. CL mem allocate host buffer tells the runtime to create a buffer in the host accessible memory, whereas CL mem use host pointer is to tell the runtime that it's going to use the supplied host pointer as the storage for the buffer. And this will prevent the redundant copies of data, especially in the APU environment. We're going to briefly talk about APU environment in a later slide. The CL memory copy host pointer together with this CL mem allocate host pointer is to say that where or how we're going to find the initial data to put into the buffer, to initialize the buffer. For both the allocate host pointer and the used host pointer, it is reasonable to assume that the implementations will have the device access the buffer from the host memory across the PCIe bus. This is very common, especially to improve the memory performance by using so-called zero copy method. So it essentially use a space that is on the host side or on the device side and use memory mapping so that both can access that part of the memory. This is not explicitly required by the OpenCL specification, so depends on the actual device. Vendors may have different implementation. Host accessible memory has a very interesting implication. Let's say for example, AMD specific treatment of these flags, they leverage APUs, which is a tightly integrated CPU and GPU architecture. These two processors share memory space. So this CL mem allocate host pointer and CL mem use host pointer will be essentially the same because if the device supports virtual memory, which is the shared memory space between the CPU and GPU, the storage will create as pinned host memory, and they will be accessed using zero copy. If no such virtual memory is enabled or available, then storage will be allocated on the device side. Also, there's a new flag called Use Persistent Memory AMD. This is a vendor-specific extension. Will ensure that the access to this memory object from the host will be directly to the device memory. So there will be no copies on the host side. When you use these memory flags to store data, you want to make sure that you understand the performance implications of your choices. We can use one other technique called mapping to make it easier to access data on the device. OpenCL provides such a mechanism for the host to access the data without going through explicit read and write API calls, and also to avoid data copying. And these APIs are called CL-INQ map buffer, and on the other hand is unmap memory object. When we use CL-INQ map buffer, what the OpenCL runtime attempts to do is to provide a pointer to the host side, and so that the host can use this valid pointer in the host memory space to access the data in the device. And it's similar to the read-writing to the buffers. Let me show you an example. So first we use CL create buffer to create a buffer space memory object on the device side. So this buffer object points to some space on the device memory. And this CL-INQ map buffer API call will take this buffer as an argument. And this API call will return a mapped buffer. Note that this mapped buffer is just a memory pointer on the host side. As if you have, let's say you do a malloc on the host side, and that returns a valid pointer. So this pointer can be then used in a similar way as you create such a pointer using malloc. So all the following operations that performed on this mapped buffer will in fact take place in the device memory. But to the programs on the host side, it sees this mapped buffer as just a regular pointer in a host memory. In other words, this buffer, this memory object, is mapped to the host's address space. Once the necessary memory copy operation is done, or any computation is done, we can then use CL-INQ unmapped memory object to release this mapping. So as a result, there will be no valid pointer from the host memory space pointing to the device buffer. In new OpenCL 2.0 specification, there's a new concept called shared virtual memory. Shared virtual memory is to extend the global memory to the host memory region. The major benefit is to allow the addressing to share the host in all devices. More concretely, we want the device to be able to access the data that's on the host and may not be in the sequential order. For example, we can pass pointers-based data structure as argument to kernels. Pointer-based data structures are, for example, linked list, trees, graphs, and kernel can then operate on such linked list. Without having this shared virtual memory, the kernel cannot work on such linked list spread across the memory, because in that case, the pointers given to the kernel is invalid for the kernel to access, because the pointers are addresses in the host memory space. With this shared virtual memory, the kernels can use these pointers of the host memory space to find the right data. There are some detailed options of shared virtual memory at different granularities, and then their OpenCL object is slightly different, and the allocation methods and consistency model is slightly different. And if you're interested, you can refer to page 6.1 on page 159. This is an example of doing shared virtual memory allocation. It takes the context and the first argument with possibly some flags to indicating the granularity and the size and the alignment. This SVM alloc will return a non-null if the allocation of the shared memory is successful. And after that buffer is used, we can then free the buffer. Images are different in buffer in several ways. They are opaque data types that cannot be viewed directly through pointers. And these are multi-dimensional structures and have limited range of types for graphics data, rather than being free to implement any arbitrary data structures. Image objects is to offer access to special function hardware on graphics processors or on FPGAs to support highly efficient access to image data. There are specific filtering operations that can allow efficient transformation of the image data based on the pixels. Pipes are new memory objects in OpenCL 2.0. They are essentially first in, first out FIFO type of structure. They are primarily used to pass data from one kernel to another kernel, so that within a device, two kernels can share a region of memory and then guarantee the protection of this shared state. This implies that devices that support pipes must support atomic operations, because these FIFO operations have to be atomic. Also must have a memory consistent model supports acquire and release semantics. And they can use specialized memory different from the main memory. And currently we do not allow host side operation on pipes.